Okay, so here we are on Tuesday, September 22nd. Semester is peeling right away. We got to get through STEAM because we got two other big blocks of the course, so I'm going to be pushing hard. On this homework that you're assigned, you're to evaluate a variable frequency drive on the boiler fan. I think that's a 125 horsepower fan. And so one way you can do that is there are calculators out there, and I think it's fair game. So if you look up on my screen, I'm about to go to the ABB. They're a big, I think they're German or they're a European company, but they produce some really nice products. VFD fan calculator, okay? And so I'm gonna go there. And let's see, I'm gonna go down here to this ABB Save Energy Calculator. Maybe. Let's go ahead and minimize this. And of course, it's Tennessee Tech, so the Wi-Fi is slow. Okay, so they have these things that are kind of tailored for different typical applications. One would be for fans, pumps, or air compressors. Okay, and a variable frequency drive allows this fan to run with speed control. It's an electronic device, a power electronic device that basically changes the frequency. It takes the input power at 60 hertz and breaks it down and puts it back together at different frequencies. And you also have to change the voltage to it, but we don't, mechanicals don't really care about the internal workings of it. We care about the fact that it'll save energy for us on the fan control, okay? And so if you click on this guy, you can get up here, and it's got a basic approach to it and a more advanced approach. Okay, and so I'm going to let you guys investigate this, but this calculator will calculate savings for you. I really suggest, I think the advanced is really better. You get more control of what you're doing. And so basically what you're going to do is you're going to look at your boiler is making, well, you're going to determine how much steam your boiler is making. That's part of the homework, okay? And then, so you can assume that's pretty constant. So let's say it's making, 75% of its rated load. I gave you a rated load, I think 250,000 pounds an hour. So let's say you're making 2/3 of that or 3/4 of that, 75%. Well, if you got 75% steam production, you should need someplace around 75, 80% of your fan capacity. And in reality, the fans are usually oversized significantly. So even at full load, the fan has more capability than it really needs because they don't want to wind up short on air. So they usually upsize the fan on these things. But anyway, so you have to make an estimation of the engineer as to, well, I think this fan only needs to put out 75% of its rated capacity. And so then that gets you down in here into some of these numbers like, okay, what percent of full flow am I going to analyze? Because what that VFD is going to slow the fan down to the point that it produces that amount of flow. Instead of, you're told that you have discharge dampers, which are very inefficient. The discharge dampers just add resistance to the airflow and forces the fan up the fan curve, which does reduce the airflow, but it's not very efficient in terms of the electrical energy that the fan actually uses. Okay, so that's what we're getting at. So I'm going to point you here, and I want you to think about this some on your own too. And you can get out there and look at other resources. Do a little research on your own as to fan dampering versus speed control. All right. So that's a pretty good hint on that one. All right, let's see where I want to go. I want to go here. So this is where we left off in the slide. So we've got a couple of slides here about save energy by reducing steam demand. And so I think what's going to happen on your steam trap, you're going to calculate a rate of loss from an individual steam trap. You have a population, and you're to assume that 2% of the good ones fail every year, and it's been 5 years since they've looked at them. So you can run through a calculation. You might want to do it in Excel or something and figure out how many of those traps are failed, and then what the loss rate is for those traps. And then so that's how much steam you're losing. And then you can run a reduction in steam demand in the measure tool in order to evaluate that. That's like, because those leaking steam traps, the ones that are blowing to atmosphere, just blowing into condensate return, that's kind of like a steam leak. Okay, so you can assume that's however many pounds an hour that you're going to save by fixing the steam traps. You can then run a project in order to reduce your steam demand by that amount. And so you've got some of those traps on the high pressure header, you've got some on the medium pressure header, you got some on the low pressure header. So you have to reduce the appropriate steam demand at the appropriate pressure in order to evaluate it. Okay. So in a plant, steam demands, it can take on all kinds of forms. I mean, what are you using steam for? It can be any number of things. Reducing steam consumption can often result in the most significant energy reduction opportunities. So we want to eliminate inappropriate steam use. Maybe we're using steam for something that is just stupid to use it for. Or maybe we're not using it very efficiently and we can reduce the steam demand. So here's a little example that we run through here. So we've got a process that requires air to be heated to 120 degrees Fahrenheit. So right now, this air is being taken from outside, and over the course of a period of time, the inlet temperature to the heater is 40 degrees. Okay, and so the coils in this HVAC unit are being supplied 20 psig saturated steam. So that's probably our low pressure header. And then, we've got, so we got 20 psig saturated liquid condensate that's condensed in those coils that goes to the traps, that then goes to the condensate return system. And the airflow is 10,000 standard cubic feet per minute, okay? So that's what we're doing. And so we're going and, you're wandering around the plant looking at things, and I say, well, what is that? Oh, that's heating up air to go down here because we got to blow that in on this process. Well, where's the air come from? Oh, it comes from outside. Well, anytime you go in an industrial plant, the air up close to the ceiling is usually quite warm. You go in a boiler room, and it's usually 100 to 120 degrees up there, especially. I mean, even in the wintertime, it'll be like 85 or 90 because all the heat loss from the boiler and the equipment, where's that? That's hot. Where's it go? It rises up to the ceiling, sits there at the ceiling until that heat then gets transferred to the roof and goes out back to Mother Nature, So one thing we do on boilers is we want to pull combustion air from the warmest place we can get it because that's less fuel input. Well, this is kind of a variation on that. So somebody makes the observation, gosh, maybe we could pull this thing off the roof where it's, the process requires air, just a second. Okay, so this is I'm getting ahead here. So this is the calculation on how much energy that we're using right now. And so just m dot Cp delta T, back from your thermo days, that's pretty simple. So m dot is the volume flow rate, the 10,000 times the density of the air, 0.074 pounds mass per standard cubic foot, 0.24 specific heat, Cp for air, and the delta T. So we're currently using 254,200 BTUs an hour. Okay, so then the observation is, hey, let's pull this air from inside reuse some of this waste heat before it just gets lost in the environment, and we won't have to put as much steam into the coils. You know, pretty simple idea. So, you know, you run around, you take some measurements, and you say, wow, this is summer, what's it going to be in winter? And you talk to everybody, and everybody kind of has a big powwow, and you know, says, oh, let's use 65. Okay, let's use 65. You know, that's a round number, but you know, it's at least indicative, ballpark kind of thing. So you redo the calculation, and we actually could have changed, I guess, the density a little bit, but we didn't. Anyway, so you got 120 minus 65 instead of 120 minus 40. And so that comes out to 587,300 BTUs an hour, which is 70%. So that's a 30% saving by simply doing some ductwork changes. Instead of pulling it outside, you know, cap that off outside, cut a hole in the duct inside, put some louvers in there or something so it can pull some indoor air in there, and bingo, there you go. Saves 34,000, 250 pounds mass per hour of steam. See, and we don't calculate, we don't show the calculation of that, but you know, what do you got? You've got saturated steam in, so you know the enthalpy of that. You got saturated liquid out, so that's the delta enthalpy. And you know how many BTUs per hour it's going to save, so that's going to tell you how many pounds mass per hour. So it's pretty straightforward calculation. And then you apply your steam cost to it, and bingo, 34,000. Okay, let's go on to combined heat and power. You guys got a bunch of turbines that you have to put in your model, and that's the combined heat and power discussion. So that's another term for CHP is cogeneration. Yeah, so what cogeneration means is that we're going to have one fuel input to the boiler, and we're going to get two useful energy streams out. One is going to be steam or thermal, and the other is going to be electrical energy. So basically what we'll do is we'll take that steam, we'll run it through a turbine, we'll drive a generator, and then we'll come out of the turbine with enough pressure and enough temperature that we can then drive our process uses. And so then we condense the steam as part of the process, and we don't throw hardly anything away. It's a very efficient way to operate. So we're going to go through some discussion of that here. So combined heat and power cogeneration activities almost always include an aspect of power generation, electricity. It may be beneficial to explore the most common method for power generation. Okay, so this is going back to what the utility. This is what a utility does. It only makes one product, right? They make a TVA makes electricity. They don't produce dry wood. They don't produce anything else other than electricity. So, you know, they're kind of a one-trick pony, you might say. So they put the fuel in the boiler. They make a high pressure, high temperature steam as they can for a given plant. They put it through turbines. They drop that pressure at the exit of the turbine as low as they can get it. It's usually about 1 psi-A. So they pull it down to vacuum because they want to get every iota of power they can out of that turbine to put into the generator to make electrical power that they sell, you know, to distributors and large customers directly. And then the steam comes out of that turbine and goes to a condenser where they throw that heat to the lake where the old retired guys go to fish in the wintertime. That's about the only other benefit. You know, in the summertime, too bad, the water just gets warmer than it would be otherwise. It's too warm and the fish go someplace else because it's too warm for them. Okay, so approximately 50% electrical power produced in the U.S. is produced from our standard power stations burning coal. These days, that needs to be updated. We're probably down to 30, 35% coal. As you know, there's a big war on coal for the emissions and the CO2 and all that stuff. But back these slides, that slide was probably made 10, 12 years ago, and it probably was 50%. back in those days. Okay, so this is data from '09, but I have recent data. When you take the steam power plants class, I always give out some of this stuff. And so I'll email this out to you. But this is kind of interesting. This shows for electricity net generation, the government, EIA, Energy Information Agency, compiles all kinds of statistics. And so you can see for the electrical industry, how much was generated and what was the fuel source annually. And then in the most recent, so we got to be a little careful. We don't want to go too far. There we go. We can see, let's see, they've got 18. But if I put 18 on there, you can't see the headings. So we'll pull down here in a minute when you get used to it. But so you can see, you know, coal peaked, what, 07? What's that, 2,016,000, and what's the units on this? The units on this are million kilowatt hours. So that's 2 million kilowatt hours. So wrap your head around that. Write out all those digits. There's a bunch of zeros there. But anyway, so you can kind of see. So that first one is coal. And so in 18, let's see, do we have 19? I've only got, on this one, it's only got the 9-month total for 19. So they've got through September. Yeah, but I don't have a total over here, so you'd have to do the math. So you can't really see, but see, it's dropping. Coal's dropping from 2 million. There's 1.5, 1.2, 1.1. I'm sure it's down. So you can see it's probably about in half from where it was at the peak. And then you can see petroleum. Petroleum's expensive energy. So you don't expect to see a whole lot. The people that generate with petroleum do it because they don't have another choice. And so it tends to be kind of flat. If you can get out of it, you're not going to use it. But sometimes you can't get out of it. So you just, you know, bite the bullet and go ahead and burn it. Then you can see natural gas. Look at the increases in natural gas. I mean, it's just as coal has gone down, natural gas has come up. You know, and this year, what is it, 05, where we, 07, where we had over 2 million kilowatt hours. The natural gas was not quite 900,000. The natural gas in 18 is up to almost 1.4 million, and the coal's down. And that's fracking. Fracking has made natural gas cheap, and it is now for new generating assets, natural gas is the go-to fuel. Unless they're going to invest in renewables. It is kind of interesting. So let's just, so other gases, this would be maybe blast furnace gas or coke oven gas, industrial gases. Nuclear tends to be pretty stable. You can see 805,000, 805,000, 807,000. And of course, that's a 9-month total. So nuclear is pretty flat. If you've got nukes, you want to run them because the fuel's pretty cheap and there's no emission. You know, if there's any emission, it's a real bad day. Something melted down. But by and large, most days, 99.9% of the days, there's no emission. You know, there's some thermal. They give off some heat because it's a steam cycle, but there's no CO2 or anything like that. What about what? The materials. What about the materials? It's got some way. Well, no, they just put it in a cask and put it in a swimming pool, and it has to sit there for what, 15,000 years. My brother Yeah.
They've got storage
Yeah.
facilities that are the size of 10 football fields.
Oh, yeah.
5-gallon drums.
Basically, they keep them in water, I think.
It's crazy.
It moderates it, yeah. Well, you know, nothing's perfect in life.
I think I'd rather have the CO2.
Yeah, but anyway, you know, I tell people, and I mean, I'm an environmentalist at heart, but I'm a practical environmentalist. And, you know, we joke around a lot in the steam power plants class. I tell people it's not easy to be a tree hugger because you can't figure out what it is that you want and what it is that you don't want, you know? Well, you don't want coal. Everybody pretty well agree on that. But do you want nuclear? Well, back in the day, you know, they didn't like nuclear, but then we got on climate change, and they sure don't want CO2. And so you can have coal or you can have nuclear. See what I'm saying? It's not easy to be a tree hugger, you know. You gotta pick your battles. And then comes along cheap natural gas. Well, you really don't like natural gas, but you like it better than coal. And so, you know, the US has drastically reduced emissions in the last probably 10 years. And it's because we went off of coal and went on natural gas. Well, that's good, but we're still burning hydrocarbons and we're still putting up CO2. It just puts up, natural gas puts up about half of the CO2 that coal does for the same amount of power generation. So we're moving in the right direction, but you know, we still don't want to do that. Well, do you want to do nuclear? Oh no, we really don't want to do that. Well, there's no CO2. Yeah, but we have this waste problem, and they cost God knows how much money to build, and they take God knows how much time to build. It probably takes 15 years to get a nuclear plant in operation. It takes 5 years plus to get the license to start building it. You know, so I mean, and there's like every weld has to be x-rayed at least once, if not 2 or 3 times, and all those have to be filed away. In a coal or natural gas plant, hell, just weld it up, it'll be fine. You know, if it's a nuclear plant, oh no, we got to take 5 x-rays of it, you know, and store all that away. So it's a whole nother game. Anyway, so those are our fossil fuels and nuclear. And then we got the ultimate renewable, hydro. Well, except, anybody heard of the snail darter? You ever heard of a little fish called the snail darter? They stopped nuclear plants in East Tennessee because there's some little fish, about yay long, like a big minnow, and they swore it was only in East Tennessee, and it was going to become extinct if we built any more dams because it destroyed its habitat. And so they canceled hydro projects that would have built dams that back up water that allow for renewable generation. Again, it's not easy. None of this stuff is easy. But anyway, so hydroelectric is the largest renewable that's conventional hydro. Well, what's this pump storage? I got a negative number on that. That's where, what is it, Raccoon Mountain? Ever heard of Raccoon Mountain down around Chattanooga? There's a mountain down there that the top of it's hollowed out. There's a lake bed. And so at night, when power's cheap, they pump water up and they fill up the lake. And then about 10 o'clock in the morning, when power prices go through the roof in the summertime, they open up the valves and the water falls down through the turbine and they generate electricity. But overall, it uses more to get it up there than they get back when it comes down. But the price when they pump it up there is small, and the price when it comes down is big. And so they make money. So that's pumped storage. And then conventional, that's just the dam. But look how big that number is, my goodness. Compared to, there's biomass, you know, sawmills have wood chips and, you know, paper industry and all that stuff. They burn a bunch of wood and wood waste. Geothermal, You know, you can tap into Old Faithful. Something like that. But there's places around where the Earth's crust is thin enough that they can actually pull heat from the center of the Earth, but it's pretty small. Solar and wind. So now start looking at your fossil fuel totals and your solar and wind totals. So what, solar in 16, now we can go down because solar's going up because there is a lot. I guess 17, we got 18, let's see, solar's this third column. So in 18, it's 63,000 versus 4.174 million. Why don't we just go all to solar? A lot of solar collectors. Okay, what about wind? So you see wind, that's the 272. Well, that's a much bigger contributor. So the wind, let's say if it's 4.2 million, what, 1%? What is that? If we move it to two places, what is it, 400,000, 40,000? So, you know, what is that? I don't know, 5-6% wind? Is it that much? My math isn't good. But anyway, you can see of the total, it's still pretty small. It's growing, but before we totally rely on renewables, we got a long way to go. And you know, you don't see many windmills around Cookeville, do you? Wonder why not? Oh yeah, the wind doesn't blow. So we're kind of out of luck, as they say, in terms of wind power around here. It's not going to work. So then that puts us down to solar. And does that sun still go down every night? Last time I checked, it still gets dark at night. You know, so it doesn't generate much. But you know, you guys don't want any electricity at night, do you? No, you don't want to take a bath at night with hot water. No, you don't want to do that. You don't want to run your computer at night or wash and dry your clothes or, oh yeah, keep your food cool in the refrigerator. It's okay if all that stuff goes off at night, isn't it? So anyway, I mean, I'm being a little facetious, but you know, this is, I like to give people the overall kind of view of power gen. Everybody is absolutely encouraged to have their own opinion and become informed. In fact, I have some interesting articles, you know, short things, 2-page little blurbs that I'm going to send you all shortly. I just haven't gotten them scanned yet. Okay. So if you look at individual component efficiencies at, you know, just say a coal power plant, what would they be? Well, these TVA boilers are like 100, 120 feet high. They're like 5, 6 stories. And they got every component, every whiz thing imaginable. So they get 90% efficient. You know, because it makes sense, because they put so much energy through there. It's a good investment to buy all of the extra little things, you know, economize, you know, whatever you can do, recover heat and all that sort of thing. Okay? Turbine isentropic efficiency, 85%. Oh, that's great. Smaller ones might be 50, 55, 60%. So they've got the best boiler efficiency. They've got the best turbine efficiency. They've got the best generator, 99+% efficient. So what's the overall fuel to power conversion efficiency? 35%. Whoa. That, pardon the expression, but that kind of sucks. And you know what? That's on a good day. That's on a good day. Now, modified cycles, supercritical, stuff like that, really pushing the envelope, 42. Combined cycle can get 55, 60, something like that, where you have a gas turbine and, you know, something more complicated than just this simple. Well, that's not very good. So why is this so low? Pray tell. Oh, in the condenser, we're going to throw away 50% of the fuel energy? Dadgum. That does not sound like a good plan, does it? We're going to burn this coal, and half of the energy we're going to put in the lake so that the retirees can catch fish in the wintertime. That's their plan, isn't it? That's how they designed it. No, it's just that when they pulled that pressure down so low coming out of that turbine, the temperature is only about 110 degrees Fahrenheit. But most of the steam is still, most of the fluid, the working fluid, is still steam. While steam at 100 degrees still has a lot of energy. It's still 1,000 BT, 1,000, 1,100 BTUs a pound. It's a bunch of energy. It's 100 degrees. It's 110 degrees. What are you going to do with a boatload of 110 degree energy? You're going to put it in the lake or the air because you can't do anything with it. So they're locked in to a 50% loss in the condenser. And then they've got stack loss, and you know, they got heat losses, and they got other losses. Wow. Well, let's look at an industrial facility, much smaller scale, you know, boilers and turbines. So our boiler, you know, on a good day, we're 85%. Our turbine, decent sized turbine, might be 70% isentropic efficiency. Generator is not as good, 95%. So what would be the overall conversion efficiency? Guess what? We can approach or exceed 70%. Well, how can we do that? Because we're going to use the energy coming out of the turbine in the plant. So we're going to generate at a higher pressure and temperature than we need, steam in the boiler. We're going to put it through a turbine. We're going to get electricity that's going to go towards running the plant. And then we're going to come out of the turbine, and instead of going to a condenser and heating up the lake, we're going to take that energy out to the process and make soup, make shingles, dry wood, whatever the plant wants to make. Baby food. Oh, it's a Gerber's plant. Isn't that sweet? There's no telling. Okay? And so we can use almost all of that 50% that gets thrown away by the utility company. And that's the power of cogeneration. Okay, utility stations, some like in Europe and Russia and places over there, they will heat the town. They'll come out of this turbine with enough pressure, temperature, you know, 200, 220 degrees Fahrenheit, whatever, that was a little over 100 degrees C. And they will circulate that out to the town, and people take that into their houses and heat their houses with it in the wintertime. That's fine. At least you're not throwing it in the lake, you know? So that's called district heating. So, you know, but the key is to come out of that turbine with enough pressure and temperature that it's still useful. So you've not just optimized the turbine, you've optimized the whole process, the whole plant, taking into consideration that I have to have enough temperature and quality in that energy coming out of the turbine that I can use it for something else productive. So that's the key. Okay, steam turbine fundamentals. So we'll go through these pretty quick. You know, steam turbines, they convert thermal energy in the steam into shaft energy or torque, shaft power. This shows a high pressure turbine. Those two little balls with the little arms and legs connecting it, what is that supposed to indicate? The governor. That's right. See, that thing spins around. That's a mechanical governor. And so that thing would spin around, it would be geared to the shaft. And so it's set so that when it's going the right speed, those balls extend out, the centrifugal force pulls them out a certain amount, and that controls the steam valve through linkages. And so if it starts going too fast, they go out too far, and then they'll cut back on the steam a little bit. So that thing adjusts. So that's a pretty good depiction, better than I could draw, a governor. But so we got high pressure going in. And see, we have a number of stages. When you first come in, there's a control stage, and then you have a rotating blade row and a stationary blade row, and a rotating blade row and a stationary blade row. As you work your way down through the turbine, pressure drops across each stage, and then we eventually exit at the end. We take the shaft, connect it to a generator, making electricity. Okay, so there's different types. There's a topping turbine, which is what we think are also called a backpressure turbine. And that's what we typically use in cogen, because it means the topping means that we get the electricity on the high pressure side of the cycle. And so we go in, maybe we're 600-800 pounds coming out of the boiler. We drop it to 400 pounds in that turbine, drive our generator, and we got 400 pounds to take out to the plant. An extraction turbine, you can drill a hole in the side of some of these turbines. And so maybe if you come in at, say you came in at 1,000, you could drop to 500, and you could take some steam out at 500 and leave the rest of it in and maybe go to 200. And so an extraction turbine has more than one exit, and every exit has a different pressure associated with it. We'll see some pictures of that. Straight condensing turbine, that's what the utilities use. They come in at a high pressure, a higher pressure. They take it through the turbine, get it as low as they can, and then they just condense the steam at the end of it. There's an extraction condensing turbine. So you have extractions, and then the final steam goes to condenser, and then you could have multiple extractions. So, let's see, this is steam inlet, exit. That shows more detail. And we go into this a lot more in the steam power plants class. That's a high pressure turbine figure. Shows flow over blade rows. The nozzles are stationary, and then the rotating blades are connected to the turbine rotor that spins. Shows a cross section. That's an opposed flow rotor. So this steam is coming in. That's probably a low pressure or medium pressure rotor. The steam comes in and splits and goes both directions. And they like to do that because that balances the axial thrust. If all the steam is going the same direction and all these rotors are bolted together, the whole train wants to go that way in a big way. And so you get some coming, pulling this way and some pulling this way, and it kind of balances the thrust in the axial direction. So that's a reason for doing that. That's an up-close picture of that's a TVA rotor. I don't know if you can see, some of those trailing edges of the blades are eroded away, where they have some solid particle erosion going on right in through here. You can see these things, those particles have come off of the, it's magnetite, Fe3O4. It's like a corrosion product that forms on the inside of the piping, and it comes off in little chunks and bits, and they kind of sandblast the blades on the way through. And some units have more trouble with it than others. If it gets bad enough, then they have to go in and replace the blades. See little chunks taken out. This one's kind of eroded up a little bit. Interesting. We have seals, Labyrinth seals. We're not going to go into detail. That's looking down a high pressure, intermediate pressure, and two low pressure rotors all bolted together on the same train. And that at the end of it, that's the generator down there. Okay. So back to the more detailed definitions here. Backpressure steam turbines. So the real characteristic is we come out with the exhaust pressure is much greater than atmosphere, and it's high enough to be useful. So you can have small ones. Tennessee Tech over here runs their boiler feed water pump with a little Copus single stage turbine. little bitty thing. It's about yay big. I got pictures of it someplace. I'll try to do some. About yay big. You know, it's got single inlet, single outlet. It's like this first one over here, real simple. And it just, the thing's been over there for years and years and just keeps on humming. Occasionally they do a little maintenance. They've actually got 2 of them. So they don't have to run electric motor to get feed water in the boilers. Larger ones will be multi-stage, more power and more efficiency. The more stages you have, you typically get more efficiency, but the cost of the unit goes up significantly as well. Just some more pictures. I kind of go, every once I go nuts on turbines every once in a while. So here's the extraction turbine. So, you know, we come in through the governor valves and all that stuff. We go through a stage or 2, and then we have this extraction port. So we've reduced pressure some, but it's not nearly as low as it's going to be over here at the exit of this thing. So then this comes out, and there's valves on it. They can control the amount. And so they take this off. So, you know, if this is 1,000, maybe you've got a high pressure use that needs some 500 PSI steam. So you take it off here, and then you take the rest of it down to 100 or 200 and take it on out for other uses in the plant. So that's what the extraction is all about. Now I priced one of these things one time compared to one of these, and these boys are expensive. So, you know, for general industrial use, you don't see too many of those. And if you do see one, it's going to be a big plant. It's got to have a lot of steam, a lot of power to pay for an extraction turbine. I mean, it like more than doubled. You know, I mean, it stunned me how much, when I forget what vendor it was, probably Drescher Rand or somebody. I contact one of their salespeople for some assessment we were doing and say, hey man, we could do this and do this, and we have an extraction here at this and this many pounds an hour and all this. And he said, okay, I'll work you up a price. And the price came back and we all went, whoa, they're not going to be doing that anytime soon. You know, it was just too expensive. But I mean, you do see them. There are applications for them. Another picture, extraction type turbine. Show some valving and all that stuff. Condensing, we simply pull the pressure down as low as possible and it'll be 2-phase coming out of this. It'll be wet. You'll have 5 to 10% moisture. The rest of it's steam. Again, 1,000, 1,100 BTUs a pound goes to the condenser, just a heat exchanger. I mean, it can be an air-cooled condenser. We'd like to do water-cooled because we get lower temperatures, and the lower temperature, the more efficiency you get out. And so that's probably lake water being pumped through there. And yes, they have to clean those things all the time because they get all kinds of crud. They get fish in there. They get potato chip wrappers, you know, anything. They try to pull that stuff, you know, because they're sucking water out of the lake. There's no telling what they're going to pull out. They try to filter, screen all that stuff, but I mean, they open those things up and they say there's just no telling what you're going to find. Let's see. I think I pretty well covered that. Just another picture. Okay. God, it doesn't get any better than this, right? First law of thermo. So we're going to go into the first law for and second law for turbines here. So, you know, that first 0 over there on the left, that's what? DECV/dt. That's the transient term. So we're going to do steady state, steady flow. So we get to set all that equal to 0. So what? That's the net heat transfer, Q dot, minus the net work, and then the flow terms. So for a turbine, well, we typically have one inlet, but we could have more than one exit. So what? At each inlet, it's the mass flow rate in times, you know, enthalpy plus kinetic energy, V squared, N over 2G plus potential energy, and then over the exits. So the energy passes through this turbine so fast that the heat transfer is insignificant. And they put insulating blankets on them anyway, mostly I think for personnel protection. because that steam is probably in that turbine for, I don't know, so many tenths of a second. I mean, it doesn't have time to lose much heat compared to the amount of energy that's flowing through there. So, you know, it's very, very common, and they almost always throw away the heat transfer term. And so, you know, I mean, it's typical to throw away kinetic potential energy. And so you wind up with that bottom equation. This is getting nicer and nicer, easier and easier. And so if you have, you know, one inlet, one exit, then the shaft work is the mass flow rate times H in minus H out. I mean, golly, it doesn't get much easier than that. Now, if you've got an extraction turbine, you just have, you know, you have to break it down into the amount of steam before the extraction, because, you know, you're pulling steam out midway through. It gets a little more complicated. So the thermal energy that comes out of the steam is converted into shaft energy. So, you know, pretty simple equation. And what you'll find from a first law efficiency, that these things are almost 100% efficient. So what that says is that the amount of energy that's taken out by the turbine is almost all turned into work. But the problem with the condensing turbine is there's so much energy left in the exiting steam, and then you throw it away. But that's not on the turbine. That's on you and or whoever designed the plant. You know, they just didn't have an efficient concept in mind when they designed this thing. So yeah, this is where we say, you know, if you take that shaft work divided by the mass flow rate times the enthalpy difference, it's approximately 100%. Well, what's the point in calculating an efficiency when you always get 100%? It's not very meaningful. You don't even have to calculate. Go, oh, that's almost 100%. Duh, I've been down this path before, you know. There's no point in it. And it's because there's almost no losses. When that thing gets up and spinning, that turbine rides on a film. There's no metal-to-metal contact in that turbine. If there's metal-to-metal contact, you have a big problem. Something's going to melt or fall apart in a big hurry. So all the bearings and all this stuff, they have oil pumped into them, and that thing starts spinning, and it comes up on that oil film, and so it's riding on that thin film of oil. You know, this thing might be 20 tons, spinning 3,600 RPM with no metal-to-metal contact rotationally. I mean, it's, and they've been making these things for probably 70, 80, 90 years. Tell me some of those old boys weren't pretty good at machining things. And the old ones are probably better than the new ones, you know. There's some real craftsmen out there. But so these are the losses: bearing friction, a little bit of heat transfer, and gland losses. Those are the steam seals on the end. I mean, it's all trivial, you know. So from a first law perspective, we get 100%. Well, so the efficiencies that we noted before are what? Isentropic efficiencies. And hopefully you remember this concept from your thermodynamics. But an isentropic efficiency compares a real turbine to an ideal turbine that has no losses. Okay? It's the same inlet condition and exit pressure. But so the ideal turbine is going to operate at constant entropy. And the real turbine obviously has an increase in entropy because of friction and, you know, turbulence and dissipative losses going through. So that's where we're going with this using the second law of thermodynamics. So this perfect turbine defines the maximum theoretical amount of shaft power that could be produced based on the laws of physics. This defines a perfect turbine which would operate isentropically, which means with no entropy generation. So we're going to pull our second law into this. Well, the equation's still not bad. So, you know, it's the actual work out of a real turbine divided by the isentropic work out of an ideal turbine. And so, you know, that's set up to be less than 1, right? Because the actual turbine is going to produce less work than the perfect turbine. And so once you plug it in, it just comes out to be that enthalpy ratio, HN, which is the same for both, H at the exit for the actual, and H at the exit for the isentropic. So you form those differences, you do the division, and that gives you the isentropic efficiency of the turbine. And so, you remember a good old TS diagram, my goodness. This doesn't get any better than this. There's the old saturation dome, compressed liquid, subcooled liquid, critical point, superheated vapor, 2-phase in between the dome. These are isobars, lines of constant pressure coming across the dome. And so we've got vapor, 2-phase, and liquid over here. Makes your heart beat glad. So if we look at, you know, a simple, basic Rankine cycle, I mean, this is like Thermo 101 stuff, right? But it's still got the basic components. We got a boiler, we got a steam turbine, we got a condenser, we got work coming out, and we got a feed water pump. And say we have to condense this stuff because you can't pump a vapor. You know, you can't use a compressor. They take way too much energy. But you can move a fluid, and because this is, you know, pure water that it's already hot, relatively hot compared to ambient. It's already cleaned up. It's got chemicals in it. You know, it's gone through our water treatment process. We can't throw it away, and the only way we can get it back and reuse it is to condense. And so then we got a feed water pump. We put a little bit of work in the feed water pump, and then there we go back in the boiler, put some heat in, and around the cycle we go. So if we're coming out of the boiler with saturated vapor, we're coming out at 1. Isentropically, so this we drop straight at the same entropy to 2, and then we condense from 2 to 3. We pump from 3 to 4, and this is basically an isobar from 4 to A and on up here if we want to superheat. So that's our simple cycle. Now, you know, in the power industry, we're going to superheat for sure. So we don't stop here. We keep heating. We come up here into superheat land. And then we would drop down. And, you know, if we get low enough in pressure, we'll enter. And this shows 2-phase, mostly vapor, but a little bit of liquid. If we're all the way over here, the quality is 1. So the quality is 0.9, 0.95, whatever here. And then we condense. So if we're superheating, it's 1', 2'. If we've got saturated steam coming out, it's 1 to 2. But this is ideal because these processes are straight down at constant entropy. So this is the ideal turbine. Okay. Now, we want to do that analysis on our, compare an ideal to a real turbine. And so this is, I think I cut this out of the thermo book or something. But anyway, so we've got, you know, an isobar up here, 3 megapascals. And we're going to drop down to 50 kPa. And so you see the ideal turbine comes down to the state 2S, but the real turbine winds up over here. And so this would be the exit enthalpy of the real turbine. You have to evaluate at state 2. The exit enthalpy of the perfect turbine, you evaluate at 2S. And so you have the same inlet condition. So you just got to find, you know, for a given situation, you just have to find the numbers and plug them in. Okay, questions? We're on a roll. Okay, so I think I've said all this, you know. You just, anytime you hear an isentropic efficiency, you're comparing a perfect device to a real world device. You can do an isentropic pump efficiency. And so if it produces work, the perfect one will produce more work. If it requires work, then the ideal will require less work. So on a pump, you put the isentropic pump on top and divide it by the work into the real pump, because you want that to be less than 1. So you got to set it up to be, so if it's consuming work, then you want the ideal on top and divide by the real. If it's producing work, then you want to switch that, be like the turbine, because the ideal turbine is going to produce more work than the actual turbine. So you got to swap those things. And once you understand the concept, you don't even have to write down the equations, because it's usually just the enthalpy difference across them. So it's pretty simple. Okay. So, I mean, what can that be? Well, you don't see many as bad as 15%. I've seen them 35, maybe 40 for a small single stage. But the big ones do get up to 85%, something like that. So the major contributors, turbine design, control valve, which is a discussion beyond this class, and then turbine load. Generally, single-stage turbine operate with lower isentropic efficiency than multi-stage turbine. The bigger turbines with multi-stages are better. Backpressure turbine performance. Okay, so if you look at the boiler efficiency, so we're assuming 80%, and the cost per fuel, then you can look at the backpressure turbine power impact cost. So what does it cost you to generate electricity? So we're saying at $2, at $2 a million BTUs, 80% efficiency, that translates to $8.50 per megawatt hour. So you got to move the decimal point 3 places to get a kilowatt hour. So what is that? $0.0085 per kilowatt hour. Well, that's pretty cheap. That is pretty cheap. That's less than a penny. Okay. And then at 4, you can see. So even at $18 a million, which is, we're paying what? We're paying 3 to 4 most places, maybe 3 to 6 for small places. And you can see even at 6, that's what that's 2.56 cents per kilowatt hour. So to get a kilowatt hour, you got to move it 3 places. 1, 2, so it's 0.0256. And 0.02 is 2 cents, so that's 2.5 cents a kilowatt hour. It's pretty cheap. You can't buy it. You can't buy it for that, in other words. So that shows what a good deal this is. Okay, backpressure turbine economics. So let's see. Primary factors impacting impact cost for electricity. And by impact cost, the next one that you buy or the first one that you save. What's the value of that? It's not the average, but if you save 1 kilowatt hour, how much money does that put in your pocket? That's what we mean by impact cost. Impact fuel cost. If I have to buy 1 more unit of million BTUs, how much am I going to pay for it? Boiler efficiency, steam turbine efficiency, and steam demand. Okay, so I guess we got slides here. Impact cost. Actual economic impact of increasing, decreasing electrical consumption. Average cost of electricity is typically not the appropriate value. Thorough understanding of electric rate structure. But you guys are now experts on electric rates, so you understand rate structures. At least a lot more than you did before you came in here, hopefully. Okay. So let's look at a Turbine-PRV evaluation. Assume that the site has a turbine generator set operating with an isentropic turbine efficiency of 32%, which is not terribly good. Determine the economic incentive associated with operating the turbine generator compared to passing steam through the pressure reducing valve to satisfy the thermal demand. Okay, so these are our options, and we've still got $10 a million fuel, boiler efficiency 84%. We're going to do it for the whole year, and so we've got two paths. One, we can go through the pressure reducing valve, or two, we can go through the back pressure turbine. Okay. Purchased, the electrical price is 7 cents a kilowatt hour, 32% on the isentropic efficiency. Thermal demand is nominally 30,000 pounds per hour of 20 PSIG saturated steam. And so that thermal demand is 35.5 million BTUs an hour. Saturated liquid condensate is discharged from the load at 0 PSIG. So that's kind of our parameters. Side-by-side comparison. So if we look at this, so we've got 400 PSIG steam superheated at 700. If we go through the PRV, 30,000 pounds an hour. PRV steam discharge temperature is 659. Okay, what's the first law say about going through a pressure reducing valve? This is the easiest application of the first law. You should remember this one, because if you throw away kinetic potential energy, which we usually do at this level, HN is equal to H out. We kind of talked about that in terms of spray on the PRV. You know, this is not spraying. And so the enthalpy in is the enthalpy out, but you have lower pressure. And so, but you're not taking any energy out in the valve. That's the point. You're simply changing pressure. And so what that does is it drives you a little further into the superheat region. Yeah. Okay. I think we're through that one. Okay, so now if we go through the steam turbine, steam temperature out of that steam turbine is 505 degrees. That's interesting. Does that make sense? Well, here I've got a device that's constant enthalpy. All the energy in equals all the energy out. What about here? Is that steam turbine taking some energy out of that steam flow? Daggum right it is, and it's converting it into shaft power, which is turning that generator, which means I get 505 degrees Fahrenheit. Is that likely to change my steam demand? Because see, if I still need, I haven't changed my process, I need 35.5 million BTUs an hour to my process. Well, guess what? I used to have 659 degree steam. Now I have 505 degree steam. If I still need 35.5 million, what's going to happen to my steam flow to the process? It's got to go up. So that's something that we expect to see. That's another reason we use the modeling tools. Because if I make that an assignment and make you go calculate it by hand, you're going to say bad things about me behind my back. That daggum, I spend 3 hours in those steam tables doing this crap. Oh, but I'm too nice for that. I'm going to give you the measure tool. And you're going to program this in measure, and bingo, it's just there. It just happens. It's magic. No, it's not magic. It's conservation of mass, conservation of energy, and a nice software tool that calculates all that stuff for you. But you have to understand what's going on. And so this is the previous tool that the SSAT. One of these days I'm going to not be lazy and go and do all of this and measure and cut and paste those figures and put them in here, but that hasn't happened yet. So in this one, you answer these questions. Do you wish to add a high pressure, low pressure turbine? And you click the box and pull down and say, yes, I do wish to add a turbine. Software says, okay, buddy, you got it. Okay. Select a mode. Well, fixed operation. I'm going to tell it how much steam is going through there, and then it's going to put that much steam through there. Well, what's the isentropic efficiency? Oh, 32%. That's actually a hard question if you don't really know. I mean, it's not, you have to just guess something, or really you have to go to a manufacturer and give them your conditions, and they will tell you what isentropic efficiency their turbine has. And the two different vendors may have a different answer. So anyway, and then so the fixed steam flow, there's my 32,000 pounds an hour. So notice I'm 32,000, whereas when I started this thing, I was 30,000. See, that's that extra 2,000 pounds an hour because I'm pulling energy out of the steam. I have to supply more steam to get the same energy. Okay, so this is what SSAT looked like. This is with the PRV control. So in this case, we had 90,000 pounds an hour going through. This is the pressure reducing valve. And then this one, so this one was going from 400 to 150, and this one was going from 150 to 20 PSIG. I'm passing another 49,000 pounds an hour through this guy. I don't have any spray coming in. You see the temperatures, all of that. Even with this going on, I'm still generating, I've got 150,000 pounds an hour going through this turbine, producing 3351 kW, and I've got that same amount going through this turbine, producing another 4159 kW. So I'm producing, what is that, about 7.5 megawatts, and still putting all this steam through a PRV. So see, when you go, if you go in a big plant, that's one of your first questions. How much steam goes through a PRV? Because that PRV steam, that's lost opportunity. That's exergy destruction. If you're always putting 90,000 pounds, well, look, I'm putting 150,000 pounds an hour through this guy and getting 3.3 megawatts. Well, gosh, I've got 90,000 going over here. Why don't I have a bigger turbine? And I'll get more megawatts. It's a good question. So that's kind of what this is getting to. We're gonna increase these turbines. Okay. So now this is showing, and let's see, another thing that shows over here. Let's see. You see the thermal load on the different headers. It's a little hard to read, but over here, you've even got, well, let's see. So this is the amount of steam. This includes trap losses, 20,800, but this is 18.7 million BTUs going to the process. This one is 39 million BTUs per hour going to the process. And this one is 172.3 going to the process. Yeah, and say between the two cases, the process steam load in terms of BTUs per hour is constant, because the top one is 18.7, it's 18.7. The second one is 39, it's 39, and the bottom was 172.3. So see, we're keeping the same amount of energy, even though the steam flows may or may not change. Let's see, this one is 41. Yeah, see, this one is 40 to the medium pressure is 41,000. This is 41,300. This one is 171.5. This one is 172.9. And that's because I've kicked extra turbines into operation And so I have to make more steam to provide the same thermal energy to make the same product. Okay, so now, so I kicked in this guy and I'm putting 32,100. I'm not sure why. I think we were trying to put 32,000, but anyway, it came up this. But anyway, so we're going to get 700 kW out of this. And say my PRV steam goes down by 30,000. And this one goes down from what, I forget what it was. It was 49, I think, something like that. So anyway, this thing is doing the full modeling for us of the system. And this is the same code pretty much has been reprogrammed into Measure. So you have access to this. It just looks a little different. So on the impact, looks like we're going to save 132,000 overall. So power cost is going down 393,000. Fuel cost is going up. Oh, that's the other thing. We didn't look at overall steam generation. So say steam generation with the PRV is 260. It's right here under the boiler. 260,900. Here is 263,000. So I have to make more steam, which makes sense. Well, okay. So that's going to cost me 258,000 more in fuel cost, and also 3,000 a year more in water cost. So when I do all the calculations, it nets out 132,000 in savings. So you can see. So our import power is down 642 kW, which is 4.3%. And that's what's saving us all this money. We're not buying so much electricity. Okay, most industrial systems require thermal energy. Turbine will extract some energy from steam, convert it into shaft power, which makes electricity. Result will be an increased mass flow of steam required to satisfy the thermal demand. So that's what that example was kind of put together to illustrate. Okay, so we can play around and see the impact of isentropic efficiency. So wow, on that new turbine, what was I, 32? So I run 70, and now all of a sudden I'm getting 1.533 megawatts, or 1,533 kW of additional electricity. Look at my boiler. My boiler load is up to 265,700 from 263. And so, you know, I'm pulling out more energy, especially, you know, and this steam winds up in this low pressure header. So this guy winds up going up. So this is now 175,100 has to be supplied there. But my savings, now I save a little over 900,000 in power cost, 591,000 additional fuel, 8 water, so I net out 309. Pretty nice project. Well, let's see what happens if I increase the price of fuel. So I was $10 a million, which is way high. If I go to $15 a million, guess what? My savings go away because I'm spending just about as much on the additional fuel as the electricity is worth to me. You know, so that's not good. What if the price of electricity goes from 7 cents a kilowatt hour to 10 cents a kilowatt hour? Well, all of a sudden, that 132,000 savings goes to 300,000. So I say there's a sensitivity. So in Cogen, we talk about this as spark spread. What's the difference in the value of electricity compared to the value or to the cost of natural gas compared to electricity in the same unit? Okay, so on this, if we, and I think we did this before, but for the electricity, if you take $1 million and divide it by 3412 times the electrical cost, is like in dollars per kilowatt hour, so times 0.07, at 7 cents, it's $20.52 a million BTUs for electricity, and we've got $10 fuel. So it's about a 2 to 1. But if I divide by 0.07 times 0.1, if I go to 10 cents, then I've got $29.31. It's almost 3 to 1 spark spread, which is going to drive my cogen, make my cogen look a whole lot better. And so, okay, and then if we change that $70 a megawatt hour to $40 a megawatt hour, then I lose money because the electricity that I'm generating doesn't save me much. Doesn't save me that much because I'm not paying. I'm only paying 4 cents a kilowatt hour instead of 7. So you can run all kinds of different. So indicate critical importance of parameter accuracy, Turbine-PRV. So anyway, that just summarizes all of those cases. So you can see electrical cost, fuel cost, isentropic efficiency, how much power we get, and how much it saves per year. So, I would say a rough and dirty number for cost of this thing, it depends on, a lot of it depends on your electrical infrastructure and what you have to do to integrate this generator into your switchgear to be able to absorb all this electricity inside the plant. But, $1,500 a kW, someplace between $1,200 a kW and probably $2,000 a kW on the project cost is probably reasonable. I think I told you guys to use $1,500 a kW. So if I take 1,500 times, on this first one, I've got what? 642, I'll say 650 to round it up. That's 975,000 divided by 132. That's a 7.4 year payback. That's not very good. You probably wouldn't do that. If you had the second, or we did the second scenario, maybe a little better. Let's see, 1480 times 1,500 divided by what? 309. That's still 7 years. So it's hard to get. Oh gosh, my internet is unstable. It's hard to get a great payback on this stuff. But again, it depends on the spark spread. These days, if I could buy this gas at $3.50, oh my goodness, these projects will fly at 7 cent electricity, which is probably about right. So that's probably where this plant would be sitting today. Probably between 3 and 350 per million on fuel, and probably 6 to 7.5 cents on electricity, depending on where they are. Condensing, how are we doing here? I'll tell you what, why don't we stop here and we'll finish up the turbine stuff next time. I think you guys should have pretty much enough to work on to finish that homework. Give it a good college try, and if you can't quite get it done, we take it a little bit later, but you need to be working on it for sure. And have a great rest of the day.